Okay, let's take a look at the questions that you had from 13-1. Yes, there's music playing in the background. Enjoy that. Let's start with number 11 here. Use a table of values to estimate the value of the limit, then use some sort of a graphing device to confirm your result graphic. Oh, look, a graphing device. I'm sorry, let me back up to sneak preview of everything that's coming here. Oh no, let's. All right, I'm sorry. Let's. So here for number 11 is our x plus 4 over x squared plus 7x plus 12 graph. Um, Again, we know if we're attempting to find the limit as x approaches -4, we substitute -4 into the expression there. We're going to get 0 over 0. That's an undefined value. You can't do that. So what is the limit of the function as it approaches? Well, again, they asked for a table of values. So hopefully we remember the lovely shortcut Control T to get to a table. But unfortunately, the default setting on our table here, we're going to have to mess around with that because it just goes by integers. And oh, would you look at that? Both -4 and -3 are undefined values. Gee, I wonder why. So to mess around with the table, we'll go to the menu button. And again, very limited options. We choose option 2, table, and then we'll go down to number 5, edit table settings. And again, we want to know what's happening at -4, so I'm going to start there. And then the tab button, let's say rather than whole numbers, let's go to the tenths place and see what it reveals. So if we go from -4 and take a look at some of these values to the right of that, -3.9 and such. And then let's go back to the calculator and maybe get some of these on the left side. And let's compare, shall we? See if I can get this to line up a little bit better here. Almost. All right, so what are we noticing as we're approaching from the left? The value for our function here, -0.7, -0.77, -0.83, -9, sorry, 0.91. And again, the -4 is undefined. So as we're going from each successive term here, the values are getting larger and larger. We go back to, say, -3.6, 3.7, 3.8, -3.9 to -4. These values are getting smaller and smaller, but it looks like both of them are heading towards the same value of -1. They're asking you to use a graphing device to confirm the results graphically. So back to this, again, Control T, so that we can remove the table. Well, that was an impressive little jump. And again, we're looking at what's supposed to be happening here at -4. We're saying it's a limit here of -1. Yeah, I think the graph, what your calculator screen will show you, will verify that. It's a little quirk of the Texas Instruments calculator here. We can zoom in on that and get closer and closer. It's an undefined value. There should be a hole in the graph if we were drawing this, but the calculator is programmed to estimate the value of the closest pixel. So in this case, again, sorry, I can do this much easier than you guys can with your handhelds. Occasionally you can see depending on how I do this, it looks like it's trying to put a hole in there. It's trying to make the values jump. Um, but if you're just looking at the static graph here, there's no way you'd be able to tell that. And that's okay. In case you're interested, sneak preview of things to come later. Yes, there's a way that we can do this algebraically. But for right now, we're just looking at a table of values, trying to estimate that either from the numbers here or from the picture. Okay. 15. Ooh, you remembered the natural logarithm, right? So here's our graph for, I'm sorry, I forgot what number that was, 15. So again, a lovely couple of asymptotic portions of it there. So we're looking for the limit here as x approaches positive 1. So again, if we go to our table, change the values here under 5, the table settings, again centered at 1. I'm going to take this back to zero point 0.1. Again, we know that that value is undefined. So from the right, 0.472, 0.478, 0.485, 0.492, and on the other side, 50851. Okay, so it looks to me, by our lovely table of values here, that we're headed towards 1/2. And again, a visual inspection. Come on, there you go. For the value of 1/2, I'm sorry, value of 1 for x, it looks like it's heading for 1/2 on the y. Yeah, there's no kind of trickery, there's no kind of foolishness going on there. So we should be okay. All right, 19. A wonderful thing here, trying to get you to understand this whole concept of a limit here from a visual standpoint. For part A, looking for the limit of g of t as t approaches 0 from the left. So I don't know why, but I'm going to say left is yellow. So if we're getting closer and closer, again, where t is equal to 0, that's basically the y-axis. As I get closer and closer to the y-axis, this value gets lower and lower, and it looks like it's headed towards a value of -1. As I approach that same value of t, though this time from the right, again, arbitrarily, right is green. So if I'm following the graph here from the right, headed down towards 0, it looks like I'm headed towards a value of, oh, wait a minute, -2. Those are not the same number. The limit of g of t as t approaches 0 does not exist. Again, it's because those left-handed and right-hand limits are not approaching the same thing that the limit at that value does not exist. Okay, for part D then. The limit of g of t as t approaches -2. I'm sorry, 2 from the left, +2. So again, here's 2 on our t-axis. I start tracing the graph here from the left, heading towards the value of 2. It looks like our function here is getting closer and closer to the value of 2. If I approach 2 from the right, that means this way, it's decreasing, and it looks like it's headed towards a value of, oh, wait a minute, that's 0. So again, the limit of g of t, when t is approaching 2, does not exist. And then just so that you make sure that you understand how how to read the graph itself, not looking for the limits. For part G, it just wants to know what's the value from the graph of g of 2 from our graph. That's 1. It's this value right here. So as we approach the value of 2 from the one side, we're heading towards 2. As we approach from the right, we're headed towards 0. But the actual value on the graph here is a positive 1. Now let's contrast really those for what's happening here at 4. If I, again, approach from the left and head towards 4, it looks like I'm headed towards the value of 3. From the right, as I approach the value of 4, hey, look at that. Those are headed towards the exact same value. This limit does exist. This is equal to 3. So again, I think this is a wonderful illustration here of left-handed and right-handed limits have to be the same in order for the limit to exist. That's the graphing part of it. All right, use a graphing device to determine whether the limit exists. If it does, estimate it. What's it equal to? Okay, so where did I put this? A cubic function divided by a quadratic function. I'm guessing I put it there. Oh, yeah, my goodness, look at that lovely. I don't know, looks roughly hyperbolic. It isn't, but again, with the differences there in degrees, kind of reminds me of that. And again, we're looking for the value as the limit as x approaches 1. So control T. Oh, look at that. For 1, it's undefined. What's happening here on the right-hand side of it? Okay, I'm not sure if we need to really mess around with the value of the table here. 5758. Oh, look at this. Because again, as we're approaching 1, there's a dip, and then it suddenly, sorry, let me get this out of the way. We've got this part where it comes down, it's decreasing, and then there's a sudden shift, and all of a sudden it gets very large very, very quickly. So again, at 3, it's 6 2/3, and at 2, it's all the way up to 13. Okay? So this looks like as we're getting closer and closer to 1 coming from the right, that's headed up to where? Positive infinity. But here, if we trace this approaching -1 from the left, again, it's increasing and again takes a sharp turn and then it dives down. So for the part here on the right, it's going way up. The part here on the left, it's going way down. Are they headed to the same value? That's the key thing here. That limit does not exist. Okay. So we don't have to worry about the second part of it there because there's no way to estimate that. But wait a minute. If we're supposed to be looking for the limit as x approaches 1, and we just rely on our table there, again, there are limits to what the graph on the Texas Instruments calculator can show us. Maybe we should dig a little bit deeper, like we've done with the other ones. And again, we're looking for the limit as x approaches 1. And just like we've done before, I'm going to change that to 1/10. Now again, there's the value of 1. It's undefined. But wait a minute. These numbers here are very different from what we just saw a moment ago. That's because 1.5 is another undefined value. We would really have to mess around with that window to be able to see the top and bottom parts of it there and see that. Now again, hopefully you can understand this concept here. Because the denominator is squared, it's quadratic, If we take that expression here, we set that equal to 0, there are going to be two different values of x, where our denominator is going to be equal to 0, which is going to give us an undefined value. Okay, so once I've switched the table to the tenths, we can find, yes, just as we expected here, 1 is one of those undefined values, but 1.5 is the other. And there were really strange things that happened here. Now, again, we saw at 2, it was 13, so it had come down and then started going back up again. Without looking closer here, at least the tenths place, we would have missed that other. Oh, and then look at that. On the other side of that undefined value of 1.5, we get these values between 1.5 and 1 from the right that are consistently negative, and on the other side of it, it's also negative. Okay, so one of the big things that you're going to learn to look for in calculus is, as you're going through, is there a sign change? Well, in this case, once we dig a little bit closer, at 1, there isn't a sign change. It's negative on the one side, it's negative on the other. Well, okay, what's the limit? Maybe instead of just going to the tenths, say 0.05. Now let's see what's happening here. Negative 5.17, negative 5.7, negative 63, negative 709, negative 911. I'm not sure. I mean, we could average those and say, what? Looks like it's headed to about negative 8. But let's zoom in a little bit more here from our table, say 0.02. Oh, I'm sorry. I messed that up because I was at the wrong spot. Let me try that again. We want the table to start at 0 and 0.02s. There we go. So there's our undefined. So from the right, negative 9.9, negative 9.3, negative 8.9, negative 8.4. From the left, negative 6.6, negative 7, negative 6.7. Are we convinced yet? Say I do this one more time here. Again, I want it centered at 1, and I go 0.01. Yeah, I know. I heard some of you screaming, "Why'd you do that, Mr. Mark? Just go from 0.1 to 0.01." Yeah, I have my reasons. Okay, so in this case, the actual value here on both sides of, again, at 1 it's undefined, but on either side of 1, they're both negative values. There is no sign change there, and that does definitely not show up on our graph. So looking at it's approaching from this side, it's approaching from that side, we really should say this value is in fact negative 8. That one kind of threw you off, didn't it? And that's why you asked, and that's why I answered. We work so well together. All right, now let's see if I've got for number 5. Oh, look at this lovely thing. In a lovely shade of, I don't know what that is, getting ready for Easter. The natural log of sine squared of x. Now remember, with your calculator, you've got to type it in a little bit differently than the way it's printed in your book. Okay? So you've got to put a set of parentheses around sine x and square it. A set of parentheses around that and tell the calculator to take the natural logarithm. So we're looking for the limit here as x approaches 0. All right. Now, are we going to get fooled again? In this case, again, we know that this is undefined. Now this one, if you'll indulge me here, is just a little bit different than the one we just looked at. It looks like on the negative side, all right, let's adjust our table. Let's be consistent with this. Let's start at 0, and let's change that to a tenth in between each step. So from the right, the numbers are getting lower and lower. From the left, it looks like the numbers are getting lower and lower. And yes, would you even say that there's a certain amount of symmetry to it? So if the values from the left are headed towards the same values, the same value coming from the right, then this would be a consistent thing where we get the same value for the limit. So my question to you is, what is that number? Both from the left and from the right, they're headed towards what? -4, -5, -6, -7, -9. If we keep doing this over and over again, table settings as 0.001, what number are they headed towards? Because on the positive side, it's now -13, and on the negative side, it's also almost -14. Let's add another 0. Now is it headed towards, goodness gracious, -15, -18? Where does it end? Oh, the madness. No, I would say from the left, it's heading towards -infinity. From the right, it's heading towards -infinity. What number is the limit here? I'm sorry, I meant to write that in red here. I'll do it like that. Infinity is not a number. Infinity is not an actual number. It's concept, it's a description of things that might happen. You can't say the limit is -infinity or the limit is positive infinity. If it is tanking, there is implied to be, with our lovely graph there, a vertical asymptote. And if they don't converge at the exact same value, the limit does not exist. If they don't converge to the same exact real number value, the limit does not exist. All right, how about cosine of 1 over x? Wasn't that fun looking, kind of a seismograph something going on there? Now in this case, we're looking for the limit as x approaches 0. So I don't know if we want to zoom in on the window here for once. As it approaches 0, how about we go from -1 tab, +1. I don't know how far here. I don't know, say -5 to +5. Ooh, look at that. It got even worse when I zoomed in a little bit here. Maybe not so symmetric and not so pretty after all. I want to look at that even closer. say negative zero point 0.1 to positive zero point 0.1. I don't know if I'm going to leave those 5 and negative 5. I guess I could have zoomed in on that some more too. Yeah, the nice smooth cosine curve there starts getting really wonky. All right, now part of this is the Texas Instrument Calculator trying to fill in pixels to graph what it's limited to a finite number of pixels to our trustee table. Okay. So again, I'd say let's just go to our table settings. Let's start this at 0 and let's go a tenth. And again, you really can't see it with the graph, but I think something very similar is happening here as with the last one. It looks like there's a certain symmetry to it. 0, always remember to reset that. Yeah, it's positive, it's negative, it's positive, it's getting smaller. Oh, did I do it again? I didn't reset it to 0 here. Oh, look at that, there's another sign change. There's sign changes all over the place here. Again, the smaller and smaller the number you pick there, again, our function says, if you can see this over here, 1 over x. We put a ridiculously small value in for x. We're going to take the reciprocal, which means the cosine is going to be an equally ridiculously large number, and just small steps are going to give us huge differences here. But again, with the table, we can still see that it has symmetry. That's an indication here that, again, at this value, we have an asymptote. So we would be able to say then, because they are not headed to a specific value, that this does not exist. All right, for the last one I'm going to talk about here, number 29, we have a piecewise function. Again, you're asked to graph it. Use your graph to find the values of these individual limits if they exist. All right, so yay, here's our graph. How do you turn this into a, if you don't remember this, go to your 9 button, and immediately adjacent to the 9 button, if we push that, well, there it is. I never ever use that fraction or that exponent thing. There are easier ways to do the roots, and you've got special buttons for E and logarithms. This is what we're looking for. Okay? Now, again, the way they've shown it to you there in the book is here's a function for this particular interval. So it's not just using this one. We need this template right here. So we have a function, comma, for this interval. Okay, so if we then just hit enter, that worked out nicely because again, there's just two different parts of it here. If you needed 3, 4, 5, if you need 7, there's a way we can do that also. So for the first one here, sorry, where are you going? it's x squared. Hit the tab button, and that should then take you to the next box here. And then I believe we can just type that in, x. Okay, so again, for the next part, it's got to be x is less than or equal to 2. Well, all right, sorry, don't hit your enter button. Now, again, the infrequently used buttons here, past the 7, past the trig, there's a button here so you can type in, we don't want the equals, don't do that. Control first, and then that button, a lovely pop-up menu. And this is less than or equal to. So that's the symbol that we need there, and then the 2. I believe we can hit tab to go down to our next function, which is simply 6 minus x. Doesn't like it when I do that, evidently. X. Hit the tab again, and then this has to be x is greater than 2. So again, control greater than 2. I wonder if it's going to like that or not. Oh, all right. It automatically converted. We're not. Oh, so we're up to orange now. All right, so for future reference, the seventh graph will be orange. Isn't that nice? All right, so now that we got the graph, kind of funky looking. All right, well, pick apart those two different components there of the piecewise function. The first part, x squared, that's a parabola. Simple parabola. Vertex at 0, 0 goes through 1, 1, negative 1, 1. 2, 2. Oh, wait, hold on. We're supposed to evaluate what happens here at 2. So as we trace along from the left, as we get closer and closer to 2, as we trace along from the right and we get closer and closer to 2, it would appear that for both of those, this looks like it's heading towards a value of 4. This looks like it's heading towards a value of 4. So yes, the limit does exist. It's equal to 4. I suspect once we have the graph, filling out parts A, B, and C aren't that challenging. It's just remembering how to do the piecewise and how to get the greater than, less than, or equal to portions in it there. All right, I hope that helps. You got any other issues, please shoot me an email. Let me know. I miss you guys. Bye. Bye.